Hi, everyone. So this lecture is our second lecture on chapter 5. And we're going to be talking about sort of more detailed practical aspects of designing bipolar amplifiers. So where we talked about last time were, concepts of input and output impedance for for amplifiers and how those are important. So today we're going to talk a little bit more about biasing of bipolar transistor amplifiers. And we've talked about biasing in the past, and the idea is that, and the reason we need biasing is that the bipolar transistor, let's say you're using your bipolar transistor in a amp stage like we're used to seeing. So I'm going to just throw some values out here. This is V out. This would be V in. When operated in the forward active mode, has a transfer function, again, that we've seen quite a bit, where when we look at the base emitter voltage, there is a exponential current dependency of the collector current. And so for this to work properly, you can't operate the transistor at either too low of a current or a too high of a current. Out here, you have just there's an exponential growth, and your current just blows up, like it just essentially have a short circuit. And here, it's basically have very little current, and you essentially have a open circuit. So what you really want to do is there's a happy medium here, and we've talked about this happy medium being probably between 650 to 850 millivolts for a typical bipolar transistor, where you want to operate this device in this region somewhere. And if you then limit the input signal that you modulate in this region, if you limit that signal to be small enough, then you can also count on the response of the current change of the amplifier to be relatively linear. If we just have a small bit of modulation here, we can approximate this exponential curve as a linear curve and get a linear response from the amplifier. So the upshot is we need to basically bias this amplifier somehow so that it's in this sort of sweet spot of operation. And in the past, what we've done is we've just drawn we've said, okay, our signals are small, our V input signal is, I don't know, say in the case of a microphone, say 10 to 20 millivolts. And we just went and drew this battery here. And we said, okay, this battery is, I don't know, we just threw out numbers, 800 millivolts. And here you go, we've biased the amplifier. But in the real world, these batteries or voltage sources, et cetera, isn't something that you can easily put into your circuits. If you can think of a battery, even the smallest battery you can think of is still pretty big, given that you might have millions of these transistors, billions on a chip, or in a circuit like in your iPhone. Imagine how many transistors you have. You can't just be sticking batteries of different voltages here and there, or voltage sources. So this is good from a level of understanding when we put this sort of battery here, but it's not a practical implementation. What you need for a practical implementation is something that is low cost, physically small, that you can, it's not going to cost you a lot to put into your circuit. And we'll be talking about those circuits today and probably in the next lecture. Now, a word about the concept of biasing. So it's not one of the important things about biasing, and biasing is probably even more difficult, I think, than the design of the amplifier itself, because what you need to do when you're designing a biasing circuit is not just have it operate in the lab one time with a lot of tweaking of somebody sitting there and sort of moving voltages around, et cetera, for the design to work. It has to be robust. And what does that mean? Well, imagine if you're making a product, and let's say the product is something like a cell phone. You can't just have your circuit work with the manufacturing tolerances being extremely tight, because you're not going to get that from your manufacturers. To get reasonable priced transistors, electronics, et cetera, from your vendors, they're going to have some reasonable amount of variation. So your circuits have to work within that amount of variation. The other thing is, you can't just have, for example, your cell phone work in an air-conditioned room. It has to work, when you've put it on a dashboard of your car on a hot day. It has to work when it's cold outside. It has to work when you're visiting Alaska. It has to work when you're visiting Saudi Arabia. So it has to work over a range of environmental factors as well. So those are all important aspects that we're going to be, deciding what kind of biasing circuits we're going to be using. Okay, so let's now talk about some background. Again, I think we've talked about this, a bit of basically DC analysis, or we can think of it as large signal analysis and small signal analysis. So the way you analyze biasing circuits is, or any circuit really, is when we're designing an analog circuit, we first do the DC analysis. So we look here at the actual circuit. We've got a couple of bipolar NPN and a PNP here. And we figure out, what the collector current, things like IC and VBE. And, we figure out, may collect the collector bias voltage to make sure this device is in forward active mode, for example. And then we do the rest of our analysis in the small signal domain by using these bias elements to figure out, again, in this curve of the large signal transfer curve of a transistor, where we are here. And we figure out these small signal parameters like transconductance, the input resistance, output resistance of transistors, and we create a much more simple sort of circuits where we're only dealing with resistors, current sources, things like that, as opposed to very nonlinear exponential curves. Again, remember we talked about op amps in a typical scenario might have 15, 20 transistors. And then, you don't want, anytime you want to design something or analyze something, you don't want to be solving 20 exponential equations at a time. So you want to be basically doing things, in a much simpler way. And that's where the small signal analysis comes in. And to do that, we basically figure out where our bias elements are. That tells us our small signal parameters. These are all as made in functions of these parameters. And we create the small signal models. Now, one thing, I think we've talked about this as well, make sure the voltage sources in small signal look like shorts. The current sources look like opens. The reason for that is small signal analysis, you're only looking at differences. So we're just looking at how things change from one level of input to another. So anything that stays constant, like a voltage source or a current source that's not changing, basically doesn't affect our analysis. So we would tend to zero them out. Another fact about small signal analysis and large signal analysis is we're counting on that we're biasing the circuit somewhere. For example, here, we're biasing as at some voltage, and we're counting on the input not being large enough. So for example, if I zoom in here, the idea of small signal analysis is that my input difference in the voltage around my bias point is small enough this input is small enough so that when I look at the output change, the output current change, I can pretend like this is a linear curve. But I can approximate this exponential, just this piece of this exponential curve as being linear. When this breaks down, if my input is, you have your input is too large of a swing. Let's say my input level, I've biased here, and my input level is changing quite a bit. It just doesn't make sense to try to model that as a linear curve anymore, because there's a huge difference between this and this exponential curve when you're changing too much. Your range is changing too much. This linear approximation is only good when the change is a small amount. Now, what's a small amount? Well, a rule of thumb, this is, a rule of thumb is that the input doesn't change the bias parameters for example, in this case, I sub C, by more than, say, 10%. So this is a way to say, for this whole approach to work, for the small signal analysis approach to work, we're counting on linearizing these exponential, these devices whose performance is exponential with linear circuit elements. And that only works when the biasing doesn't change very much. Another note that I wanted to make, again, we talked about this before, but I wanted to say it again, that this is a simplification of our notation, that this is just to save ourselves the writing of every time we have a voltage source like the supply here, VCC, instead of drawing that, we're just going to draw a line and a dash like that. So basically, this circuit, by that we mean this circuit, and just a shorthand way of drawing that voltage source. Okay, now let's talk about the different bias elements, and let's talk about an example of bad biasing, and by that we mean really no biasing. Let's say you had a microphone connected to a bipolar transistor, and let's, for the sake of discussion, say that this microphone's input change that you could get out of here was around 20 millivolts. Okay, microphones just naturally don't have a huge signal coming out of them, and that's why we're trying to amplify them. We're trying to get the voltage output to be some multiple of that. We'd like it to be 2 to 10 to 20 times higher, ideally, because the signal coming out of the microphone isn't very much. Okay, so let's see what happens if we start with some bad biasing. In this case, essentially no biasing. We just stick the microphone straight into a bipolar transistor. Okay, so let's analyze what that does for us. So let me redraw that circuit. So we have our supply voltage, we have our load resistor or collector resistor, we have the bipolar transistor. This is the output. And our microphone, I'm probably drawing that wrong. Let's see. Maybe it looks like this. I don't know what the symbol for microphone. Okay, so that's what we got. So here's the input. Okay, and then we're going to be assuming that the change in input voltage is 20 millivolts. Okay, we have also been told that the transistor has got I sub s of 6 times 10 to the minus 16 amps. Okay, so let's say I'm going to do this two ways. First one, I'm not going to use small signal analysis just to show you guys what this looks like, and then we're going to do the same thing with small signal analysis, and it's essentially the same result. But let's look at what kind of change in current we get at the output when all we have is a change in the input. Okay, so basically, if I draw the current transfer characteristics, whereas there's I sub C of this Q1 transistor, we are operating down here because we haven't biased this. We haven't biased this transistor to be out here anywhere, so it's down here, and the signal level is fairly low, so we're just moving around down here at this low end of this exponential curve. Okay, so the equation is, if you want to look at the change in current in the collector, the equation is I sub s exponential of the change in the base emitter voltage over V sub t. The change in the base emitter voltage is this change in V input, because there's no biasing, so it's just this input. There's no additional DC circuit, which is around 20 millivolts. So if I plug that into here, I'll end up with delta I sub C is 1.29 times 10 to the minus 15 amps. So, and the reason for this very, very small change in current is because we're sitting here at the very low end of the exponential curve, and we can move this voltage around, but it's like a very flat part of the curve. So there's very little change in current over here, close to 0 volts in an exponential. And so your change in current's very low. And then if I actually look at the change in output voltage, it's the change in this current multiplied by this resistor. So I'm just looking at the change now, not at the level. So just delta V out is RC delta I sub C. So it's equal to 1.29 times 10 to the minus 15 amps times 1 kilo ohm. So let's say R sub C is 1 kilo ohm. And so this delta V out is going to be 1.29 times 10 to the minus 12 volts. Okay, so so remember the definition of the gain is change in output level over the change in input level. So the output level is 1.29 times 10 to the minus 12, and input is 20 millivolts. And this is essentially 0. So we have not only haven't we gained up anything here, we've essentially basically just having a 0 output level, because this change is so tiny, this change in current is so tiny that the change in voltage it creates, I can't really even think of what kind of instrument you would need to even measure something like 1.29 times 10 to the minus 12 volts. So this input could do whatever it wants over here. It's going to be just, you won't be able to see a change up here. Okay. So it's a non-working amplifier because we didn't put a bias in. Okay. Now let's see what happens if you if we actually could had, if we did, so we want to repeat this with our theoretical, with our battery, which we know we can't use practically speaking, but I just want to show you what happens if you did manage to have a bias voltage here. So what we're doing is we're repeating this experiment and we're saying, let's take this guy and put a battery here of 0.65 volts, okay? And what in effect that does is, so the orange represents here, that's the biasing level here. And then the red is going to affect this biasing level. So let's say it puts it somewhere out here, 0.605 volts. And we're biased here, where we might get a bigger change in collector current. So again, without doing the small signal analysis, if I look at delta I sub C here, and again, my input is 20 millivolts, that this guy creates 20 millivolts on top of the 650 millivolts. So it's I sub S exponential of 650 millivolts plus 20 millivolts over V sub T. That's the highest value, so this is the max. And the min is I sub S exponential of 650 millivolts plus 0 over V sub T. So this becomes 93 microamps minus 43 microamps, and that's approximately 50 microamps. Now, if I want to look at the change in my output level voltage from this change in current, I multiply that 50 microamps times the kilo ohm, and I end up with 50 millivolts. So if I look at the gain here, so V out over delta V in. Okay, so we've got 50 millivolts over 20 millivolts is 2.5x. So here, what if I have, in this case, if I have a 20 millivolt input, I'll get a 50 millivolt output, sorry. If I have a 50 millivolt input, I get 150 millivolt output. So now by biasing this, I have put myself on a good part of this transfer curve. I've biased myself in a good part of this transfer curve, and I'm getting some reasonable gain out of the circuit. Okay, so now the question again, so that was just to demonstrate, but again, I can't in real life, I can't in a reasonable way, I mean, in reasonable cost, reasonable area, et cetera, just stick a battery wherever I want this biasing. I need to come up with a biasing circuit that I can put there in terms of cost and area, et cetera. So, well, okay, so we say like, it didn't really work to be on this bottom part of the curve. Let me extend myself out here somehow. So another thing you could think of doing is to say, well, I can maybe just hook up this output. So this is exactly like this circuit as our initial circuit, but I hooked up this output to VCC. Hook up this output to VCC, and what happens then? Well, maybe what I want to do is I have my exponential curve, and heck, I'm going to try to be out here. I'm going to be here, and I'm going to get lots of gain out of this. I'm going to bias it here. Okay, by shorting this guy to this guy, my VBE ends up being, I don't know, whatever, let's say this was 2.5 volts. And I got lots of current, good to go, okay? Well, the problem here, though, is that you do have a high voltage here, and you have, I mean, I think it's going to blow up the transistor, but if you had 2.5 volt VBE, you can imagine how much current you might end up with going through this transistor. But even more importantly, you're shorting this point. You've got a dead short between the microphone and the input. If you remember, a microphone or any kind of input, any kind of a source is going to have a source resistance of some amount. In the previous lecture, we talked about 200 ohm, an example, etc. So if you have a 200 ohm resistor from your signal to a dead short, really anything, any resistance to a dead short, you won't be able to move this point at all. It's just going to be sitting at 2.5 volts, and it's not gonna change. You just have a short, or it's going to move. There's be no modulation at the input of this device, so that doesn't work. So seeing that, the next step, you think, well, maybe what we want to do is, one, pull this up, but maybe by not that much, maybe not by 2.5 volts. And then also want to put some kind of, maybe I don't want to, let's do pull it up to some intermediate level, not 2.5 volts. Maybe want to pull it up to, I don't know, someplace where we like, let's say 800 millivolts or something like that. And we also want to somehow not have this be a short, and we want to put some resistance here in between this and this, so that this resistance, whatever this value of this resistance, can overcome that resistance. So basically this impedance is just creating a little bit of a current, and this guy's actually driving the input. And that's going to look like the simplest biasing resistor that has a chance of actually working, the biasing circuit, sorry. And that is basically implemented by putting a resistor in the between the base and the power supply. And if you had our input would go here, our microphone in this case would connect here, and because this has a as a source resistance of, again, say 200 ohms, if this is something like 100 kilo ohms, this guy's signal is gonna basically sit on top of whatever voltage we generate here, and the modulation will go through okay. And this will just sort of pulling this up to a level where this gets biased. So let's see what this equation looks like. So the input of this bipolar transistor has a certain base current. So the voltage here at X, so V sub X is equal to VCC. So this, we got the supply voltage minus the voltage drop across the resistor RB, and that's I sub B times R sub B. And so Vx, notice in this case, the Vx is the voltage of the base. The emitter is at 0. So VBE is Vx minus 0. So I can plug in VBE here. So VBE is VCC minus IB RB. And I can just rewrite this by rearranging it to have IB equal to VCC minus VBE over RB. And the collector current is just beta times this I sub B. So it's basically that gives me this value, which is just I sub B times a beta. Okay, so let's see what this looks like. Just do an example. So here's a here's a typical case, the supply voltage being 2.5 volts and R sub C being 1 kilo ohm. R sub B being 100 kilo ohm. We want to make this relatively large so that we don't fight with our potential input too much. So let's see what this looks like. So again, just sort of repeating these equations. I sub B is VCC minus VBE over R sub B, and I sub C is beta times I sub B. And then finally, we need to also check the collector emitter voltage across this bipolar transistor to make sure it stays in forward active mode. So we also need to look at the end of our calculations, double check that we're at the right level. So that's VCC minus I sub C, R sub C. So it's the supply voltage minus the voltage drop here, sets your collector voltage. And the emitter voltage is at 0, so VCA just ends up being this voltage here. That's to double check that the device isn't forward active. Okay, so let's now run some numbers. Let's assume that I sub S is 1 times 10 to the minus 17 amps. Beta is equal to 100. And we already said VCC is 2.5 volts. So, we have to start here. Now the problem is we don't know VBE and VBE, and to know IB, we need to know VBE, and to know VBE, we need IB. And so it's a circular event. So this tells us that we need to do our iterative procedure. So we guess a value for VBE. And we plug that into these equations, and hopefully we converge to a value after a few iterations. So let's guess. So guess number 1, starting point is VBE is equal to 800 millivolts. And again, reasonable guesses. So reasonable guesses for VBE when it's on is between 650 and millivolts and 850 millivolts, say. I mean, maybe a little bit less, a little bit more, but in this range. It's not going to be 2 volts. It's not going to be 300 millivolts. So we can guess something in the middle there, 800 millivolts. And then we're going to start this first iteration. So iteration number 1, we start by calculating I sub B using that VB value over R sub B. And so it's 2.5 volts minus 800 millivolts over 100 k ohm. So this is 17 microamps. And I sub C is beta times I sub B. So it ends up being 1.7 milliamps. So now we can plug this back into our VBE equation to see if this first guess was close. So that's V sub T natural log of IC over I sub S. And we end up with over 1 times 10 to the minus 17 amps. And that ends up being 850 millivolts. So that's reasonably far away from it. Remember, this is an exponential characteristic. So 850 is pretty different than 800. In fact, we said a 60 millivolt difference in VBE gives a 10 times change in current. So the current caused by this VBE and this VBE might be like 8 or 9x difference. So it's not a 50 millivolts isn't a lot, but it's still, given that this has an exponential type of function, it's not good enough. So we go through iteration 2, we plug this one in instead of 800. So iteration number 2. Now we use IB as 2.5 volts minus 850 millivolts over 100K ohm. And with that, we get 16.5 microamp. And I sub C is equal to 1.65 milliamps. And if I plug that into my VBE equation, VT natural log of 1.65 milliamps over 1 times 10 to the minus 17 amps, this is going to give me 851 millivolts. Now, thankfully, that's pretty close to our previous value. So 1 millivolt is pretty close. So we can say that these are close enough. And you can also see it in the collector current. So when 1.65 milliamps versus 1.7 milliamps, those are pretty close numbers. So we can say that's, that's the value. So in summary, we end up with I sub B being 16.5 microamps, I sub C being 1.65 milliamps, and now we also VBE being 851 millivolts, and we have to double check our VCE to make sure we're in forward active. So that's equation where VCE is this one. So it's 2.5 volts minus ICRC. So it's 2.5 volts minus 1.65 milliamps times a kilo ohm. Yep. And that gives us 850 millivolts for VCE. Okay, so these are the values we come up with. And, our base voltage is at 851. Our collector voltage is at 850. So we still have a reverse bias. We have like zero bias essentially, but it's not forward bias across the collector base region. So this tells us that we are in forward active. So we're okay. It was pretty close, but we're okay. We are in forward active. So check. Good. That worked. So it seems like we actually ended up with a pretty good solution, and a very simple one at that, because all we did is, we pulled this up a little bit, not too much. We pulled this up to 850 millivolts using just a high value resistor. And that resistor was large enough, we can put our input. So that this whole biasing thing wasn't so bad. So that's great. But when you actually look at this from a standpoint of manufacturability, it turns out it's not such a good solution. And the reason for that is because of process variations and manufacturing variations. So let's take, for example, looking at this parameter beta, which is basically the gain between the collector current and the base current. So we said beta is equal to 100. That's a reasonable nominal value that you'll see a lot in manufacturing specifications. But just like any other manufacturing process, there's some variation around this beta value. So the manufacturer tells you, hopefully you guys are familiar with like Gaussian distributions, that, okay, this is my beta value and it's centered around 100. But in fact, if I look at this as a population of transistors sold by the manufacturer, there's going to be like a distribution around this. Not every transistor you'll get from the manufacturer is going to have exactly a beta of 100. Just like, if you're buying um, like a set of screws or something like that, they're not exactly the same size down to a billionth of a meter, or like to a nanometer or something like that. There's some reasonable variation in manufacturing parameters. Otherwise, those screws or these transistors end up being extremely expensive because the manufacturer has to do extraordinary things to control the variation. Okay, so there's some reasonable variation around this beta value. And a lot of times, for a lot of manufacturers, this change, so change in beta might be 20%. So for example, beta may be 100, it might be 120, it might be 80. There's some variation around that you can reasonably expect. And you can do things like only accept, you can do, this circuit, say, hey, this is my circuit, so I'm only going to buy from the manufacturer. I'm going to call them and say, hey, only send me these transistors with a beta of 100. And they might do that, but then they're going to charge you for all these other transistors they made that didn't make that value, because they had to build all these in the manufacturing process, throw them away, and only send you this beta of 100 value. Or you would take all these, plug them into your circuit. Some of the circuits would work okay, some of them wouldn't, and you'd only be able to sell the circuits that work okay. And unfortunately, you actually see that a lot in a lot of companies, and it's basically called poor design. So what happens is, when you end up designing your cell phone, you end up having to scrap 10% of the cell phones you made, let's say. Sorry guys, I think I stopped sharing here. Just give me 1 second. I lost my internet access. Trying to reestablish here. Okay, back on. Sorry about that. Okay, hold on a second. Nope, still not out of the woods. That's 1 more second, guys. The reason actually I'm saving this as opposed to doing a live broadcast is because of where I am this week. The internet access is really terrible. Still not able to connect. Okay. Let's see. Wow. Hmm. Um, well, guys, sorry, it looks like I can't reconnect, so I'm going to stop here, and we will pick up again next week. Thanks.